Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits. In this lecture we will be talking about number systems and codes, right? So let's get started. Basically, if we have to talk about number systems, right? So basically like in digital systems, if when we talk about number system, there could be multiple things. We could be talking about binary number system, which is basically base 2, or we could be talking about decimal number system, which is base 10. One very famous number system is hexadecimal, which is base 16, and a less famous one is called octal, which is base 8, right? And once we talk about this number system, what does this number system mean, right? So since all of us are familiar with the decimal nomenclature, right? I will try to explain this number system using this particular reference of decimal number system, which is a base 10 number system, right? So if we talk about this decimal base 10 number system, what do we have usually? Let's assume that we have a number, say 548.01. This decimal point is the point from where we will start, right? 8 would be like, we would say this is like ones position, this is like tens position, this is hundreds position, and so on and so forth, thousands, 10,000s. Similarly, what we say that this is tenths position, and this is like hundredths position, and then thousands, and so on, right? So if a number is 548.01, we have a decimal point followed by tens, hundreds, and ones, tens, and hundreds. How do we represent this? So basically, ones is nothing but 10 raised to power 0. Ones, ones is nothing but is something like 10 raised to power 0. Tens is 10 raised to power 1. Hundreds is 10 raised to power 2. Similarly, tens is nothing but 10 raised to power minus 1, and hundreds is 10 raised to power minus 2. So if you see over here, right, our base is 10. That's why this is called a decimal system. Whatever this entire system is based upon the foundation of ones being 10 raised to power 0, base being 10, tens being 10 raised to power 1, and hundreds being 10 raised to power 2. Correct? Similarly, now if we have to talk about binary number system, right, let me quickly go on to another file. This is something we mentioned on decimal. Let me quickly recapture it, right? So if we have something like 548.01, this is like 10 raised to power 0, 10 raised to power 1, 10 raised to power 2. This is base 10. This is decimal point. This is 10 raised to power minus 1, 10 raised to power minus 2. Now if similar thing we have to do it in a binary number system. Binary, as I mentioned you, this is nothing but base 2. If it is okay, so decimal we said that it's like a base 10. If it is a base 10, it can have 10 digits starting from 0, 1, 2, 4, 3, 4, 5, so on and so forth till 9. If we have base 2, we can have only 2 digits, right? 0 and 1. And let's assume we have something like a number like 1101.10. In such a case, this will become decimal point, right? This is nothing but ones, so which is nothing but 2 raised to power 0. This is 2 raised to power 1, 2 raised to power 2, and 2 raised to power 3. Similarly, tenths would be basically in decimal, what we would say is like 2 raised to power minus 1. This would be 2 raised to power minus 2. Correct? Now, if we have to convert this decimal number to this binary number to decimal, what would be the value? Like, for example, what is the value over here? How do we calculate the value of the number? So we say something like 5 into 10 raised to power 2 plus 4 into 10 raised to power 1 plus 8 into 10 raised to power 0 plus 0 into 10 raised to power minus 1 plus 1 into 10 raised to power minus 2. This will be nothing but 500 plus 40 plus 8 plus zero point 0 plus zero point 0.01. This will be 548.01. Similarly, what would be the value over here? The value over here would be 2 raised to 1 into 2 raised to power 3 plus 1 into 2 raised to power 2 plus 0 into 2 raised to power 1 plus 1 into 2 raised to power 0 plus 1 into 2 raised to power minus 1. This would be nothing but 8 plus 4 plus 0 plus 1 plus you have 1 by 2, which is nothing but 0 0.5. Correct? So basically this number is 13.5, as we could see from here. So basically, this is what a decimal number system is. This is a binary number system. What we did is we spoke about a binary number system, which is nothing but a base 2 number system having only two digits, 0 and 1. And it's easier to understand if we take a reference of a decimal number system, which is base 10. Everything for a binary number system will be base 2. All the denominations and all the powers would be with reference to a number 2, and this is how we calculate a value of a number, or how this is how we convert a number from binary to decimal. Or in other words, right, if someone asks us how do you represent 13.5 in binary, so this is 13.5 in decimal. If someone asks how do we represent this 13.5 in binary, so the answer would be 1101.10. Correct? And just to let you know, right, since we call it ones, tens, hundredths, so this will be like ones position. This is similarly called twos position. This is called fours position. This is called eights position, right? Similarly, this is like halves position. This is like quarters, right? And we just saw an example already, right? If we have to see one more example of a binary number system, right? Let's assume we already took an example of 1101.10. We said this in decimal is equal to 13.5 in, sorry, this number in binary is equal to 13.5 in decimal. Now, if we have to do an exercise where let's assume we have to convert this number to decimal, right? What would this be? How do we do it, right? Just as a quick exercise. So this will be 2 raised to power 0, 2 raised to power 1, and so on and so forth. This will be 2 raised to power minus 1, so on and so forth. So basically what we will get over here is 1 into 2 raised to power 3 plus 1 into 2 raised to power 2 plus 0 into 2 raised to power 1 plus 1 into 2 raised to power 0 plus 0 into 2 raised to power minus 1 plus 1 into 2 raised to power minus 2, which would be nothing but 8 plus 4 plus 0 plus 1 plus 0 plus 1 by 4, which is nothing but 13.25. Correct? So this is the basic concept of decimal system and binary system. And similarly, right, if we have to extend this concept to other systems, right, octal systems. So let's assume we have a number, say a, b, c dot x and y. In octal number system, octal is nothing but base 8. Base 8 would mean that we will have digits from 0, 1, 2 up to 7, right? And this would mean like if we assume this is a decimal point, correct? If this is a decimal point, this particular value in octal number system would be a into, this will be 8 raised to power 0, this would be 8 raised to power 1, this will be 8 raised to power 2, 8 raised to power minus 1, 8 raised to power minus 2. So 8 into 8 square plus b into 8 plus c into 8 raised to power 0, 8 raised to power minus 1 plus y into 8 raised to power minus 2. So this will be the conversion of octal number system into binary number system, which will be nothing but 64a plus 8b plus c plus x by 8 plus y by 64. Correct? And going so forth and so like so on and so forth, if we have to think in terms of hexadecimal number system, right, which is an important one. So hexadecimal is nothing but base 16, and which means we have numbers from 0, 1, 2 up to 9. Then 10 is represented using A, 11 using B, C, D, E, and F. Correct? And there's a reason why we name it like A, B, C, D, E, and F, because it's easier to represent in them in binary. And I will talk about that. And base 16. So basically A, B, same number A, B, C, X, Y in base 16 would be equal to A into 16 square plus B into 16 raised to power 1 plus C into 16 raised to power 0 plus X into 16 raised to power minus 1 plus Y into 16 raised to power minus 2, which would be nothing but 256A plus 16B plus C plus X by 16 plus Y by 256. This is how you convert this particular hexadecimal number into decimal number with base 16, numbers being 0 to F, right? So this is the basics of number systems. So the as we see, right, base forms the basic, and depending upon base we will have number of digits in that system, and similarly we can convert any dimensions into any other dimension. Now we have a important concept, right? So basically I will introduce two terms to you. One is something called as a radix complement, and one is something called as diminished radix complement. Okay, so basically when we talk of complement, right, so complement has to be with respect to some base, right? So basically if we say that we have base 2, radix complement for this would be 2's complement, and diminished radix complement would be 1's complement. Okay, similarly for base 10, radix complement would mean 10's complement, and diminished radix complement would mean 9's complement, right? And if you have to talk about like what's the use of this complements, or like why do we do this, these are used for finding negative of a number. So let's assume we say that okay, we are representing 1 using particular digit in base 2 like base 2 system, right? How do we represent minus 1? So these radix complements and diminished radix complement help us represent a number in negative format, right? So basically as a rule of thumb, right, if a number is n, base is r, and number of digits are n, correct? So basically if I am saying there's a number called n, right, in a base r having smaller number of digits, a radix complement for that number would be r raised to power n minus capital N, and diminished radix complement for that number would be minus 1 minus n. For example, right, if we have to take an example over here, just if we should understand this perfectly fine, let's take some time over here. If a radix complement is like r raised to power n minus n, whereas diminished radix complement is r raised to power n minus 1 minus n. Let's do it with an example. Let's assume we have like a number, say 0 1 0 1, right, to the base 2. So here, right, here what is the case here, our base is 2, basically r is 2, number of digits n is 4, right, and my capital N is nothing but 0101, correct? In such a case, what I would say, in such a case my r minus n minus n would be equal to this will be like 2 raised to power 4 minus n. This will be like 16 minus n. Whereas my r minus n minus 1 minus would be what? 2 raised to power 4 minus 1 minus n, which would be nothing but 15 minus n. Correct? So what this simply means is, let's assume we have a binary number. So how we already spoke about binary being base 2, binary base 2, right? So let's assume we have these decimal numbers. What would be the equivalent binaries like? So let's assume that we have to write equivalent binaries, and let's assume we have 4 bits to represent a number, right? So 0000. So this is a basic, right? So if you see, uh, you over a period of time, you will get used to knowing like remembering like what all number corresponds to what all digits. But if you have to go by this thing, right? So this is 0. So all digits being 0, this is like nothing but 1 into 2 raised to power 0. This is nothing but 1 into 2 raised to power 1 plus 0. This is 1. This is 2. This is nothing but 1 into 2 raised to power 1 into 2 raised to power 0. This is nothing but 2 plus 1, which is equal to 3. Right? Similarly, so basically, if we convert these decimal numbers into binary, this would be the one. Now, let's assume that we have a decimal number 5, right? So let's assume we have a decimal number 5, which is represented as 0101 in binary, right? And let's assume that this is a base 2, right? Now, let's assume we have to find 2's complement of this number. What will be the 2's complement? Correct? 2's complement for this number would be r raised to power n minus n. What is r raised to power n over here? So 2 raised to power 4 minus n. 16 minus n. What is n over here? N is 5, 11. Right? And what would be 1's complement in this case? 1's complement would be nothing but r raised to power n 10. Correct? And basically, how do you represent 11 in decimal system? So basically, so this is a reverse calculation which we have to do using a LCM. But if you see, right, 11 would be nothing but 1 1 0 1 1. This is how we get it. So we divide it by 2. 2 5s are 10, 1 is a remainder, 2 2s are 4, 1 is again like so 1 0. So basically the number which is left is this one, 1 0 1 1, and this corresponds to 11. So basically 2's complement, what this means, this simply means 2's complement of 0101 is nothing but 1011, and 1's complement of 0101 is nothing but 10. If you see, 10 would come out to be 1010. Do you see some relation between this? Okay, so let me get a new file for this one, and before we dive deeper, right? So what we saw is 2's complement of 0101 is nothing but 1011. 1's complement of 0101 is nothing but 1010. This is how did we calculate this? This is like using the formula which I told you guys just now. Simply, basically, r raised to power n minus n, r raised to power n minus 1 minus n. Now, do you see a relationship between these two in for a base 2 binary, right? What is the relationship? If you see, 1's complement is each digit inverted, right? Inverted of original number, and 2's complement is nothing but, you can simply say it's like 1's complement, which is nothing but inverted of original number plus 1. right? See, if we add 1 to 1011, it will become 1011. So this is one of the important thing to remember for our digital systems. Whenever we're talking in terms of base 2 or binary number system, 2's complement is nothing but is like 1's complement plus 1, and 1's complement is nothing but it's just like all digits inverted. That is, 1 becomes 0, 0 becomes 1, right? So this is one of the important application of digital system, where we say that whenever we have to find a negative of a number, right? So basically, if you see, right, whenever we have to find a negative of a number, what we simply do is we look for 2's complement. 2's complement is nothing but negative of a number. So before we dig deep into that, right, I just want to talk about a simple thing of signed and unsigned numbers, right? So just before we go any further, so there are two concepts like unsigned numbers, and then there's a something called as a signed numbers, right? Now let's assume that we have 4 bits. Let's assume we have a 4-bit number. If we have 4-bit number, what all values it could have? All zeros, 0, 0001. I'm just writing them quickly. 1 2 3 4 5 6 7, and then we have something like, correct. So now let's assume we have numbers from 4-digit number. If we have a 4-bit number, say this is like, how many numbers can we have? How many numbers we can represent? 0 1 2, so on and so forth, and this is nothing but 2 raised to power 3 plus 2 raised to power 2 plus 2 raised to power 1 plus 2 raised to power 0, which is nothing but 15. Correct? So basically a 4-bit number can have a values from 0 to 15. This is under the assumption that all the numbers are positive. So basically, how many total number of combinations are possible for a 4-bit number? That is 2 raised to power 4, which is equal to 16. Correct? And if there are 16 possible combination, numbers are from 0 to 15. Whenever we say at signed numbers, whenever we say unsigned numbers, means all numbers are positive, and if we have 4-bit numbers, the number of possible combinations are from 0 to 15, right? And whenever we have an unsigned representation of a number, right, what we simply do is we go from minus 2 raised to power n minus 1 to 2 raised to power n minus 1 minus 1. So basically, this is just a formula to remember, or in case, right? So basically, let's assume that for a signed representation, how many numbers are possible for a 4-bit number? Only 16 numbers are possible, right? And if 16 numbers are possible, what all number of possible combinations are there? So there would be minus 8, minus 7, minus 6, so on so forth to 0, 1, 2, up to so on up to 7. Correct? Is this fine? Correct? Okay, let's quickly go through it again. So let's assume, so this is my number, right? In signed notation, sorry, in unsigned notations, this will be 0 1 2 3 up to 7, and then we have 1 0 0 1 0 0 1 1 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 8 9 10 up to 15. Correct? So but in sign notation, right, what we will end up doing is these numbers, okay, in the sign numbers, right, the MSB, the most significant bit, will represent sign of a number. 0 means positive, 1 means negative. So basically, if a sign number 0 is a positive number, if you see all the numbers from 0 to 7 are having a 0, right? So these are all positive numbers. So, and then these last three bits represent a value, 1, 2, 3, so on and so forth till 7, correct? And then eventually, right, this represents value, this represents negative, correct? So basically, this would mean the number over here in this particular case is, right, this number would become 0. Sorry, so basically a value is 0 over here. We have 0 to 7. And what would happen in this particular case is if I put all ones over here, right? So if a number is 0, what will I just told you it, a negative number will be 2's complement. What will be the 2's complement of this one is like 1's complement plus 1. 1's complement is nothing but inverting all the digit plus 1. What would be this? This would be like 1 plus 1 is 0 with a carry of 1, 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 this. So this will be all zeros. Correct? Are you guys with me right now over here, right? Or not? So in like basically, right, what would happen in such a case in signed representation? I'm hoping that this particular concept of unsigned integers is clear, like from 0 to 15. And for signed numbers, right, we go from 0 to 7, and then from when we go from 8 to 15, right, this represents a negative number. Please be with me. This is like an important concept which will be used throughout. If this is a signed number, this means that this indicates a negative number. To get a value of this negative number, right, what we will do? I already told like this is a negative number. If a number is negative, how would you know the value of this? You will do a 2's complement. What's a 2's complement of triple zero? 1's complement plus 1, which would be nothing but 111 plus 1, and this would be equal to 1000. Correct? And what is this value in positive number? Is 8. Correct? Are you guys with me? So basically, sign is negative, value is 8. Similarly, how about 001? So 001, what is, so basically 1 tells the number is negative, fine. And what is the value for a negative number to convert that to positive? Do 1's complement, 110, add 1, which is nothing but 2's complement, it would become 111. What is the value of this? This is 7. So this will become minus 7. So if you guys are with me, right? So what we saw just now is in signed nomenclature, we get number between 0, 1, 2, 3, 4, 5, 6, 7. Then we will go from all the way to minus 7, minus 8, minus 7, minus 6, so on till minus 1. So if I have a 4-bit number, my possible numbers of unsigned value are my set of numbers is 0 to 1 to 15, and my signed set is nothing but minus 8, minus 7, minus 6, so on so forth to 0, and then 1, 2, and then so on to 7. Correct? So this is a concept of signed and unsigned numbers. Basically, if you see, and this is what we will help. This is what this particular concept is what will help us in adder circuits later on. How do we do a adder circuit or a subtractor circuit? So basically, if you see, subtractor circuit is nothing but a adder circuit of positive and a negative number, and negative number is something which we will be taking as a 2's complement. Correct? Are you guys with me on this one? All right. So just to recap it, right? So we spoke about radix complement and diminished radix complement. These are nothing but these help us find a negative of a number. Correct? We have two concepts. One is radix, which is r raised power n minus n. One is a diminished radix, which is r raised power n minus 1 minus n. And then we saw an example of binary base 2 where we converted a number to a positive number to a negative number by finding a two's complement and one's complement of that particular number. Then we saw like what's a two's complement, one's complement, and how what's the relation. One's complement is nothing but inversion of all the digits for a base 2. Two's complement is nothing but one's complement plus 1. And we saw one important concept over here is that is a concept which is understood by using signed and unsigned nomenclature, where we say that if we say that okay, if we have 4-bit signed number, this would represent like the MSB, the bit number fourth would represent like, well, if it is 0 it's a positive number, if it's a negative it's a negative number, if it's 1 it's a negative number. And then depending upon whether it's a signed or unsigned, we will have a set of ranges or of the values which a particular number could have, like a set of possible set of combinations which could be there. Correct. And this is just one way of coding the number systems and number digits. I just quickly wanted to touch upon something called as a reflected code. Since we are clear of all the binary decimal notations, number system, how do we calculate values, how do we convert binary into decimal and decimal into binary, for this we did basically the approach of finding the least common multiplier. Correct. So basically what is a reflected code? If I say you, if I tell you, right, okay, so basically we need to have a set of code where when we move from one number to another, right, when we move from one number to another, only one digit should change. For example, if you see as of today, if I have a decimal number, say 3, I have four decimal numbers, 0, 1, 2, 3. How does this look like? 0, 0, 0, 1, 1, 0, 1, 1. So basically what you see over here, once I move from number 1 to 2, right, both my bit positions are changing. My bit position number 0 moved from 1 to 0, and bit position number 1 moved from 0 to 1. Correct. So this is something called as like a BCD, right? Basically what we are doing is a binary coded decimal. We are converting a decimal number to a binary. But reflected code is such that it says that whenever we move from one decimal number to a binary number, right, only one digit should change. Correct. What would this mean? Let's assume that we have a 3-bit unsigned number. So basically we will have a value from 0 to 7. Correct. If we say that okay, let's assume this is 0, 0. Now let's assume only one bit will change, so this will become 0, 1. Now if I tell you only one bit should change, what should be the answer? We can't have 0, 0. We can't change bit number 0 because we already have a 0, 0 for 0. So what it will become? 1, 0. Sorry, 1, 1. 2 will become 1, 1. What would 3 become if I say that okay, we can change only one digit? I can't change bit number 1 because it will become same as 1. So I would do something like this, right? And since it's like a 3 digit, so let's assume this thing is there, and let's move on to a number 4. So now if I tell you that we have to change one digit, what I can do? I can't change this, I can't change this, I have to change this. This will become like this. Then again, how do I go about this now, right? We have to change only one digit going forward. So what do you suggest? How do we go about it if we have to change one digit? So we can change a least LCB, least significant B, LSB. So we will change that. How about now? Bit we should change to have a unique number 101? And finally, what should we have? We should have 100. So basically this piece of code, right? If I write 0, 1, 2, 3, 4, 5, 6, and 7, if my normal binary coded decimal or a binary number is this one, say 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, what would be my reflected code? Okay, one thing, reflected code is also called as gray code. 0, 0, 0, we have to change only one bit, 0, 0, 1. Now one bit change, 0, 1, 1. Now one bit change, 0, 1, 0. Again one bit change, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0. So this is the reflected code or the gray code. And what do we do in this such cases? We are just changing one code. Correct. And if I tell you like, is there a property for this piece of code? Yes, there is a property for this number, right? If you say, if I look at the midpoint, midpoint is four numbers above, four numbers behind. Leaving the MSB, which is changing from 0 to 1, these numbers are reflections of each other, right? 0 1 0 1 0 0 0 0, right? And basically, and if you see, right, there is a specific location of reflected code or gray code in uh, digital circuits, and that is usually used for, let's assume that there is we are having multiple data transitions, and it's mostly used for data correction and data correction codes. So basically, it's often used in situations where other binary code might produce erroneous or ambiguous results during transition from one code to another. Right? So basically, if we use a binary code decimal to transmit a number 7, right? Let's assume this is our number 7. And let's assume we have a 8 also. How do we represent 8? If I have 4 digit numbers, my 7 would be this one and 8 would be. Now let's assume what is happening is, now let's assume we are going from 7 to 8. What can happen is, if at all there's a problem in one of the digits, right? One of the digits get inverted. So what could be the case is, like, if at all there's a problem where my last mode only one bit is corrupted, let's assume last one bit is corrupted, so I can eventually transfer a number called 9, which will become 1001, right? Because let's assume this is maybe because, like, this LSB takes more amount of time to change, there's some delays, right? But if I transfer using gray code, this will not be a problem, because using gray code, right, only one bit will change at a time. And that would tell me, since only one bit would change over a time, how that would tell me, like, okay, my error errors would not be there, and I could work on simply error correction. So this is like a basics of like number systems and what kind of a number systems are there. Just to quickly recap, we have binary, decimal, hexadecimal, octal. Hexadecimal is a pretty important one along with binary, and decimal is something which we can always use as a reference to generate our numbers in, like, binary and decimal format. Going forward, right, if you see, we have like decimal, base 10 we discussed base 2, and eventually we spoke about octal system, hexadecimal, radix complement, dimnixed, how two's complement is a negative of a number, how do we obtain one's complement by inverting all the numbers. Then we spoke about an important concept of signed and unsigned numbers, their ranges, and how do you convert signed number into unsigned number. And at last we spoke about reflected code, which is nothing but a gray code, and which can be used for error correction and error detection at the receiver end. Thank you.